All right, so this is section 10.1, lines and segments that intersect circles. And in this section, we begin to investigate circles and different lines that go through them and what those are going to be called. Lines, segments, rays, they're all going to have different names in relation to how they intersect circles. But first of all, we need to clarify what is a circle. We've been talking about that for a very long time, since elementary school. But you can see here at the beginning that a circle is a set of all points in a plane that are equidistant from a given point called the center. So in this first example, the center of this circle right here is P. So we can name that circle, we can call it circle P, or you can do the little symbol like that, P. Also name it circle P. And all the points on the circle are equidistant or the same distance to that point P, which is what makes it a circle because it's equidistant from that point. So moving on from there, under this core concept, you'll see that there's quite a few vocabulary words, and it can be a little overwhelming at the beginning, but you'll kind of find out that they're not really very difficult to understand. First of all, we've talked about radiuses before, or radii, but a radius is a segment whose endpoints are the center, and any point on a circle is a radius. So you'll notice right here in red that it's showing you one radius, but any point that starts at the center and then goes to the circle is going to be a radius, or radii will be the plural form. So you've probably known that. Same thing with diameter. You've talked about diameters before, but a diameter is going to be one that starts on the outside of the circle and then goes through the middle to connect to the other side. That's going to be a diameter. A chord, this is going to be a new one for you. And you'll notice over here it says a chord is a segment whose endpoints are on the circle. So in this chord up here at the top, this point right here and this point right here are the endpoints of that segment. And because those two endpoints are on the circle, that means that that segment right there is a chord. Similar to that, you'll notice that there's something called a secant line. And the secant line, it also has 2 points that are on the circle, but the secant line actually continues through the circle and doesn't end at those points. So that's the difference between a secant line and a chord, is that the chord stops at those 2 points. The secant goes all the way through. So that's a secant line. And then the last one is a tangent line and then a point of tangency. So a tangent line is going to be a line on the circle that intersects the circle at only 1 point, and exactly 1 point. So in this part right here, that is point B. It goes along and then touches at point B and then keeps going, but doesn't touch the circle at any other point. So that's what makes it a tangent line, or it could also be a tangent ray if it's just a ray that's going through, or a segment. But the main thing is that it has to only hit the circle at 1 point, and that makes it a tangent, ray, line, segment, whatever you're working on. But the point of tangency is that point where it is touching the circle, that 1 point. So in this example, that's why it's saying that point B is your point of tangency, because that's the 1 point that it's hitting the circle. Okay, coming down here a little bit further, we're going to start to talk about two circles in relation to one another. So you'll notice here that there's three different examples right here. You could have, like in this first example, where two circles are intersecting one another at 2 points. So that would be if the two circles were kind of moved into one another, you'll see that they would intersect at 2 points. On this next one, you'll see that there's also an example where the two circles only touch once. So you would see that there's a point of tangency. There's a tangent line that goes through there. That's this line right here. It's a tangent line. And the point of tangency is going to be this little point right there. So that would be 1 point of intersection. And they're also called tangent circles sometimes. And then the last one would be this example where there's two circles that don't intersect at all. That could either be because they're totally separate, or it could be what's called concentric circles. So that would be where those two circles share the same center point. So this point right here is the center of both of those circles. But of course, the radii of each of those circles would be different. The radii of this interior circle is going to be smaller than the radii of that exterior circle. Okay, and we'll talk about later on in the section a couple different ways that we can see how many tangent lines can be drawn when you have two circles. And we'll go over that in just a moment. Okay, then there's two theorems that we are going to need to know for this section as well. Theorem 10.1 is called the tangent line to circle theorem. And it says, a line is tangent to a circle if and only if the line is perpendicular to a radius of the circle at its endpoint on the circle. So essentially what that's saying is this line M right here, it's only going to be tangent to circle Q if its point of tangency is perpendicular to the point Q. So that's where you'll see why this is saying that it's a right angle. So the only way that we can say that M is going to be a tangent line is if that right angle is happening right there. And you'll see later on we're going to have to prove that a couple different ways, and we'll have to show that that is true in order for it to be a tangent line. Okay, and then also on Theorem 10.2, it's saying that tangent segments from a common external point are congruent. So you'll see right here for S, it's going to be given to us that R and T are points along this circle that are tangent points. And it's saying that this external point S is part of SR and it's part of ST. So if SR and ST are tangent, then those two must be congruent to one another. If they're not congruent to one another, then they couldn't both be tangent segments. It's possible that one of them could be a tangent segment, but not the other one. But if they're both told to us that they're tangent segments, then those will be congruent. And again, we'll see a couple of examples of that in a second. Okay, so moving down here, in this first example, it's going to ask us to tell whether the line, ray, or segment is best described as a radius, chord, diameter, secant, or tangent of circle C. Okay, so starting with segment AC, first of all. Now we'll see segment AC is this right here. It's going from the center C to a point that is outside on the circle. The only way that is possible is if that AC was a radius. And I'm sure you probably would have seen that. Okay, for B, this is segment AB. And segment AB is going from a point outside of on the circle on the outside to another point on the circle, but it's going through that center point, which means that it must be a diameter of this circle. Okay, and then for C, this is ray DE. Now DE, you can see that if we're starting at D and going towards E, and then it goes on forever, that it's a ray. And because it touches the circle only at point B and no other place, then we would know that this must be a tangent ray. Okay, be aware that it wouldn't be a tangent line because we're not talking about a line, we're talking about a ray. It wouldn't be a segment for the same reason. So just be aware of the symbol that's right here. That'll help you tell what kind of tangent it's going to be. All right, and then the last one is line AE. Okay, line AE, you'll see here's A and here's E. AE goes through the circle and intersects it at 2 points. So that's point G and point A is where it's intersecting it. But it doesn't stop at those 2 points. It continues on outside of the circle. So because that is happening, that means that AE must be a secant line. Or you could just call it a secant because it continues all the way through. And that's the definition of a secant. So, okay. moving on here, right here we have example A, B, and C, and it wants us to tell how many common tangents the circles have and to draw them. Now, you guys know I'm not the greatest artist, so I've kind of left the solution down here underneath so you can see their drawing of them all, and I'll just kind of talk you through them. Notice on A, there's a tangent that goes here, tangent that goes here, and those are going to be considered external tangents. And these external tangents, they're called that because they're here on the outside of those two circles. Over here towards the inside, these are going to be called internal tangents because they go along the inside of these two circles right here. So what the question it's going to ask you is how many common tangents do they have? And your answer is going to be 4 because there's these 2 external ones and these 2 internal ones. Okay, similarly, on this second example, on example B, there's going to be 3 common tangents. And you'll notice this is going to happen because now the circles are intersecting one another at one point. So you'll see there's going to be a point right there. So there must be 1 internal tangent and then 2 external tangents, which is what's happening right there. So that would be 3 common tangents. And then you'll notice on this last example, because they're intersecting at 2 points right here, there's going to be no internal tangents, only external tangents, which you'll see there at the bottom, it must be like that. 2 external tangents. So the answer would be 2. Okay, so now on this monitoring progress part, it's going to ask us the same thing. How many common ones are there going to be? Well, just like the ones that we just did, for this one, you're going to see, well, there must be 2 that are on the outside. It's going to look something like that. And then there's going to be 2 internal ones. So one's going to look like that, and one's going to look like this. Okay, so this one's going to be 4. There's going to be 4 common tangents on that one. 2 internal and 2 external. Okay, and then on number 4, you'll notice that because they are intersecting at one point right here, you see that along that point we could create 1 tangent line. And that line is going to be an external tangent line. So it's going to be 1, and that 1 is going to be external. All right, then on number 5, because these are concentric circles, which again means that they're sharing the same center, there's going to be no way to draw a tangent line, either external or internal. So this one is actually going to be 0. Okay, moving down here, we're going to begin to apply some of those theorems that we talked about earlier. It's asking us, is segment ST tangent to circle P? Okay, and again, the only way that that is possible, using this theorem up here that we talked about, right here, 10.1, the only way that ST can be tangent to circle P is if the point right here, T, so this segment TP, creates a right angle. Well, so the question is, well, how can we determine if that's a right angle? Well, if that's a right triangle, if STP is a right triangle, then that must mean that ST is tangent to P. So we got to ask ourselves, is 35 squared plus 12 squared equal to 37 squared? This is just using the Pythagorean theorem. Okay, well, 35 squared is 1,225, so 1,225. And we know that 12 squared is 144. And we know that, 37 squared is 1,369. Okay, and it turns out that 1,225 plus 144 is 1,369. So because the Pythagorean theorem showed that it was a right triangle, that must mean that ST is tangent to circle P. Okay, now here in example 4, it wants us to find the radius of a circle. So this point B right here is a point of tangency. So it's saying that AB is a tangent segment right there. And it wants us to find the radius. So we got to find this R right here. Now again, this may be tempting to say, well, AC must be the same as AB because of the theorem that we talked about, 10.2, where the external tangent congruence theorem. Well, SR must be congruent to ST, is what we talked about there. But we can't actually use that theorem because we don't know that this point right here is a point of tangency. And of course it wouldn't be because this line would go straight through. AC goes through the circle, so that point that it's hitting there couldn't be a point of tangency. But in order to figure this out, we're actually going to use the Pythagorean theorem, but it's going to look a little bit different. So in order to figure out R, we're going to write the Pythagorean theorem as AD squared, so that's this side, plus R squared, because that's this side, must be equal to that hypotenuse, which is 50 plus R. And that's got to be squared. So if we do 80 squared is 6,400. We're going to leave this as R squared is equal to. Now, don't make the mistake of thinking that this is 50 squared plus R squared. Okay? Do not do that. So many people are going to do that, and it's going to mess up everything for you. This is 50 plus R times 50 plus R. That's what it means to have something squared. You're multiplying it by itself. So you'll realize that once you do the FOIL method on this, that you're going to actually get 50 times 50. So we got 2,500 plus 50R plus 50R plus R squared once we do the FOIL method. Okay, and then we'll just bring these down. Okay, and then that's, when we simplify this a little bit more, we're going to have 6,400 plus R squared equals, we're going to write this in standard form, R squared plus 100R plus 2,500. Okay, and then we'll notice that there's an R squared on both sides, so we can actually subtract off the R squared. You'll be left with 6,400 is equal to 100R plus 2,500. Okay, then we can subtract the 2,500 and then divide by 100 to solve for R. So we'll do 6,400 minus 2,500, and that gives us 3,900. And then we will divide by 100, and we'll get that R is equal to 39. Okay, so that means that this R right here must be 39. Same thing with that one. Okay, so we did the Pythagorean theorem, but it just looked a little bit different because we had some R squareds in there that ended up just canceling out because they were on both sides. All right, now on this one, we're going to use properties of tangents. This is that theorem 10.2 we're going to be able to use now because it's telling us that RS, so RS is tangent to the circle C, and RT is also tangent to the circle. So because of that, we can use that 10.2 theorem that says that these two must be equal because those are tangent segments. So we can actually set them equal to one another. 28 should be equal to 3x plus 4. And now that's just simple algebra now at this point. We subtract 4, we get 24 is equal to 3x. And the x must be equal to 8. So that would be our answer right there. Okay, now I've included a couple of additional examples here at the bottom, 6, 7, and 8. I've done the work here in purple, but I'd encourage you to take the problem and work it out yourself and see if you get the same answers that I got. Just to kind of confirm that you're understanding what's happening. If you do have any additional questions, feel free to let me know. I'm either on the discussion board or you can email me. Here's your homework here in red.